Good morning, everybody. Welcome to Wednesday of ITC. Judging from everybody's enjoyment at the welcome reception last night, I gather that all of you were not silent. You exchanged a lot of data, and hopefully there was no corruption. Okay, the bad pun out of the way for yesterday's stuff. It's my pleasure to welcome everybody to Keynote session number 2. We have 2 speakers today. We'll start with a keynote address and then a visionary talk after that. So you're going to learn all kinds of neat stuff. The first talk today is going to be given by John Shalf, and he's going to be talking about the future of computing. John is the department head for computer science at Lawrence Berkeley National Laboratory, and recently was the deputy director of hardware technology at the DOE Exascale Computing Project. That supercomputing project, you might know, went on for 10 years, $3.8 billion investment, and it worked. And they hit an exaflop, the first exaflop supercomputer came online. So this is a pretty stunning thing. And this next part is the important one. One of the reasons I invited John here is, John's done a ton of technical work, 80 technical publications in the field of parallel computing software primarily, including 3 best papers and a widely cited report called The Landscape of Parallel Computing. And computing research with a view from Berkeley. And that was with David Patterson, the guy who wrote the textbook that most of us used for our computer architecture classes. And the important part, he also, before that, was part of he co-authored the exascale software study, software challenges in extreme scale systems, which sent the DARPA budget and investment direction for many years. So where goes the computer industry, and DARPA money goes the rest of the industry. So paying attention to somebody who's got his finger on the pulse of that is really important for everybody in this room. Way back in the old days, John's worked at other spots as well, including the Max Planck Institute for Gravitation Physics and the Albert Einstein Institute, where he was the co-creator of the Cactus computational software toolkit. And he went to school at Virginia Tech before it was called Virginia Tech, Virginia Polytechnic Institute and State University, way back when. So that, I don't want to date John, but he's been around in the industry a long time. So with that, we'll bring up John Shalf.
Oh, there's, okay, guys, making sure. All right. So, okay, so I'm going to talk about a little bit about the exascale computing project, but mostly about what happens next. So the ECP, Exascale Computing Project, was as he said, a 10-year effort. That this is the last year. We're going to wrap it up at the end of this fiscal year. So by end of 2023, this project will be done. But it's to develop exaflop that's 10 to the 18th power floating point operations per second. It's a full factor of 1,000 faster than the petaflop, which was done a decade ago. And the goal was to have 2 diverse systems, 50 to 100 times faster than the tens of petaflop systems that we currently have on the floor. But this 20 megawatt power peak, that was one of the biggest challenges that we identified in the 2009 report. That was a huge feat to overcome that. But the other thing is a day between human intervention. So it's okay to have a failure, but that you can ride through. But if you have 8 million processing elements in a room together, you can tolerate no more than 1 failure every 16,000 years for each processing element. It can be degraded, but it can't fail, or else our supercomputing simulations would never complete because they'd have to restart due to the failures. So that was a big deal, is being able to get to that level of self-healing and resilience that you could actually operate for an entire day. In terms of applications, I'm just going to go through this fairly quickly. What we use supercomputers for, in particular, what we needed exascale for, are material science applications where we predict from first principles the electron cloud, and from that the behavior of a material before you've even synthesized it. So that's material prediction, nuclear physics, accelerator physics, magnetic fusion. So they've built a $12 billion tokamak out in France. And if they have one bad discharge event, it'll blow a hole in the side of it, and that's 12 billion bucks. So it's good to invest in some simulation technology in order to simulate it and check for failures in the engineering before you actually build it. Additive manufacturing, so on and so forth. Combustion, more efficient diesel engines. I was talking with somebody last night about black holes, because that's actually how I got started 30 years ago in supercomputing, was developing a simulation code that from first principles using Einstein's equations on supercomputers, they built this giant LIGO in Virgo. So Hanford is the LIGO site to detect gravitational waves. This is the last big prediction that Einstein made 90 years ago that would prove out his theory of general relativity. And so they built these detectors to see if they could actually detect the time and space warpage caused by these gravitational waves. And the only thing that's strong enough to do that is the collision of black holes. And so they needed to know what they were looking for, though. What is that characteristic collision? So this is from one of our simulations 30 years ago. It took us 10 years to build the code, showing the characteristic ring made from the in-spiraling collision of black holes. And you can also see there, there's an artist conception on the top, but on the right, down the blue and red thing, that's our actual simulation that we did at Berkeley lab in 1999 of the in-spiraling collision of black holes, from which we got this diagram. And so it was gratifying when about 20 years later, somebody opened up a New York Times on an airplane, and I saw that chirp on the right there and knew that we had actually correctly predicted. Well, first off, I didn't see the headline, but I knew when I saw that chirp there on the right that they had finally seen the first gravitational wave. And they wouldn't have known what to look for if we didn't have supercomputers to simulate that. So that was what got me excited about supercomputing. But so, when it comes to getting to exascale, this was, again, a $3.8 billion program, 10 years. What we identified as the #1 target for this was, resilience was a big deal, but also getting our original prediction. If we had hit the target, they wanted to, in 2009, they wanted to hit exascale in 2018. And we realized that with the technology roadmap that we had at the time, it would be 80 to 190 megawatts. Give you an idea, a megawatt is $1 million per megawatt year. And so that would be $190 million going to the power company just to run the machine, not much less acquire it. And so we set this target at 20 megawatts. And in fact, the OLCF, the Oak Ridge Frontier System, which contains about 9,000 CPUs and 37,000 AMD GPUs, hit that target just minutes before the deadline for the top 500 list this June. And not only was it #1 in the top 500, which is the most powerful supercomputers in the world, it was also #1 in the Green 500. And there's no coincidence about that, because that was that and resilience was the two #1 challenges that we had for that program. So great. So we hit that target, exascale, and we, when we use this diagram to explain how Dennard scaling ended in about 2004, 2005. So we could no longer reduce supply voltages for CMOS chips. And as a result, heat started going way up. We could no longer grow the clock frequencies for individual cores anymore. So we started doubling the number of cores every generation for these, or having things like GPUs have extreme number of threads and cores, which led to the extreme software challenge of achieving exascale computing. But what we're looking at now is, at least we had Moore's law, which is the doubling of the number of transistors each generation of chip. This, when you see this diagram, sometimes you see that the Moore's law curve for the number of transistors is still growing, but actually that's been achieved by growing the chip area, the actual density is actually starting to taper off. And I'll show you some more diagrams demonstrating that. But, you know, now we're in this new era where we can't even double the number of cores each generation. It just means doubling the power. So we got there in exascale in 2022, but we have to ask the question, and then what? You know, we don't want this just to be the first of kind machine. We don't want it to be the last of kind, certainly. And so we have to look at what's next. Just for people who, this is another view of it. This is the top 500 list. If you look at the red line, that's the number one on the top 500 list, and that has grown exponentially for the past 30 years, where we're seeing historically 1,000x improvement every 11 years. And you can also see at the bottom, that's the last one on the list, and the top is the sum. And it's amazing how smooth that curve is, that exponential, when you look at the sum of all of the machines in that top 500 list. So 1,000x improvement every 11 years historically, but let's zoom in on the upper right-hand corner here, which is the past 7 years of performance growth. And what we're seeing now, and this is from measured performance from a benchmark that actually people argue is too easy, it's too flop heavy, the LinPack benchmark. We see now we're gone from 1,000x every decade to 10x in 10 years. And that's the future if we project forward based on the current way that we do business in supercomputing. So we have to come up with a new approach to continue scaling beyond this. And we invested, you know, $3.8 billion to get from petaflops to exaflops. There's not going to be a zettaflops program. It's going to have to be some other metric for success for driving science forward in HPC. Because we do still see, not just in HPC, but we're seeing, you know, what we used to call HPC is becoming pervasive with the needs of AI and machine learning, virtual augmented reality, self-driving cars, and remote intelligence, that we still have a 3 orders of magnitude to 6 orders of magnitude gap in the demand for compute performance and what we're able to deliver. And if you look at it from the standpoint of power consumption, right now about 8% of worldwide power goes to hyperscale data centers and the infrastructure that supports them. And this isn't, and if we continue on our current path, it's going to become something in the order of 40% of worldwide power consumption by 2040, which we cannot deliver, especially if we want to meet our climate goals. So, you know, but this isn't based on what we're able to put on the floor. This demand curve is on the demand side, not on the supply side. The need for AI, machine learning, HPC is outstripping our ability to put compute on the floor to deliver on that. So, you know, this is the 2021 SIA report. We will not meet our climate obligations if this is the path forward. So I always like to point out Neil Thompson's stuff. Neil is a really interesting guy. He has 5 postgraduate degrees. One is in computer architecture, which is why he's at the MIT CSAIL, which is the computer architecture department at MIT. But he's also got a degree in economy. And that's why he's also at the MIT Sloan School. So he has a lot of very interesting papers about the economics of Moore's Law, and also the, you know, coming up with a new economic model to move us forward. Because up until, you know, for the past 50 years of Moore's Law, it's amazing, 50 years of an exponential, totally amazing. We went from a transistor focus where you'd shrink that transistor, you get better energy efficiency and performance, which would grow the market, and you'd reinvest it, and that was the virtuous cycle for 50 years. That virtuous cycle is falling apart today. You saw from my diagram of actual measured performance of HPC systems across the world that we're no longer able to get the kind of exponentials that we used to get from that virtuous cycle. Now we're moving to more of a system focus where it's really about the integrated system, whether it's heterogeneously integrated system, that we increase functionality through heterogeneous integration and specialization to your workload in order to grow the market, get reinvestment, and create a new virtuous cycle. But this requires us to dive deeper into this co-design process. So when we talked about exascale, another hallmark of the exascale program is the discovery that you just can't simply design hardware in a vacuum and plunk it on the floor. We learned from the rest of the microelectronics industry that hardware software co-design was an essential part of that process of wreaking out efficiency. So we have to go even deeper now. We're looking at an era where we have to specialize hardware to target subsets of our workload in order to squeeze out more performance. So that means hardware software co-design is going to be software algorithms and hardware together. So this three-way confluence of co-design, and this is going to be much harder than it has been in the past, and yet much more productive in terms of being able to deliver machines under a strict power budget that can go deliver on this system-focused virtuous cycle. And some people say, oh, well, this is the computer architects are all, having a fantasy here. We know it's really expensive to create specialized machines. So a lot of the rest of this talk will be to explain that there are emerging economic models involving advanced packaging where we can bring down this cost so that it is tractable for us to specialize without doing a full custom design from the ground up, which we know is not affordable. But specialization, so it isn't just a computer architect's fantasy. Specialization is nature's way of extracting more performance from a resource-limited environment. So if you look here, you've got your powerful general purpose processors. When you have a research-rich environment, then you have these powerful raptors like the Xeon or the IBM power processor, which used to dominate the landscape of computing for the past 30 years in HPC at least. But when you get food scarcity, then those large raptors get superseded by many lighter weight animals. Like here is a couple of dozen really aggressive sparrows. Well, that's in post-Dennard scaling scarcity. That's really what the Knights Landing from Intel, what AMD's EPYC processors, many-core, Cavium, the ARM stuff from Cavium, Marvell, and also to a certain extent GPUs, which are many very lightweight threads, all cookie cutter the same, but lightweight threads, wins the day. But if you have additional food scarcity in the environment, the critters have to go after different food sources, and they evolve specialized beaks like these Darwin birds. And that's what you're seeing now with this post-more scarcity. Well, it's not post-more yet. It's just slowing down. It's not, and it hasn't ended. But you see Apple, Google, and Amazon spinning their own custom chips in order to specialize to different parts of the workload. And this is the way forward. But we need to look at how we can do that specialization in a cost-effective and productive manner. So, what we see as the future direction for post-exascale computing really is what we call extreme heterogeneity. It was like a shock to the system when we went from single core to many core, and then from many core to GPU accelerated computing in order to make our path to exascale. What we're seeing emerging in the market today, not just in HPC, but we're going to have to learn how to leverage this in HPC. What we see in the market today is actually many different kinds of accelerators co-integrated in order to deliver performance and specialization. And the research question going forward for us is, what are the right specializations to include? In particular for HPC, nobody's going to create a generic specialization for HPC. What's the cost model for that? Because we know we can't afford to spin complete custom chips from scratch. We did that back in the 1970s and 80s, and we couldn't afford to do it anymore. And so you have what's emerged is this chiplets, which is heterogeneous integration and advanced packaging, and also the licensable IP ecosystem with, Cadence and ARM and the various suppliers, where the IP is the commodity and not the chip. or even the chiplet becomes commodity. So what's the right partnership and economic model for the future of HPC? Because it really is a lot about the economic model moving forward, in addition to the technology. And so that's why I like to plug the heterogeneous integration roadmap. You know, I've been following them since their 2019 edition, but they continue to update. And this is really looking at the future. We see the future of HPC in the same way, where it's going to be the heterogeneous integration of chiplets. There's certain things, for example, in a chip that you need in any chip, you know, PCIe, memory controllers, that and some of these things don't actually benefit from being shrunk down to the latest and greatest technology node. And so by using this approach, we think that we can get the kinds of specializations we need by co-integration of these Lego pieces. So let's talk about, you know, this convergence of HPC and hyperscale data center strategies for agile specialization, utilizing heterogeneous integration to get that done. And I got a time check. Okay, so I need to be done by 9:45. Got it. Okay.
4:50.
All right.
So you got 30 minutes.
All right. So why do we want to do this? And so this is actually from DJ from Facebook, now Meta. You know, domain-specific architectures really are being driven by the hyperscalers, and it's in the response to the slowing of Moore's law, but also the exponentially increasing demand that they're facing. A friend of mine moved from HPC to work for Meta in their data centers program, and he said, we're trying to keep our growth down to 8 gigawatts. And, you know, for us, we said 20 megawatts. You know, we said put our foot down at 20 megawatts. He said 8 gigawatts. And I was like, wow, you guys have 8 gigawatts on the floor? And he's like, oh, no, we're trying to keep our growth down to 8 gigawatts. I can't tell you how much power we have on the floor. Mind blowing. So that's the scale that they're dealing with. But what they're seeing is that they're not, you know, we see this fragmentation that we already saw in the exascale era, where they went from standard computation, everybody's got an x86 or an IBM Power, to this forking off of graphics, HPC, and AI using GPUs, and, you know, in complementary with the CPU computing. And they see this fragmentation going further, again, going with that system focus, tailoring systems for subsets of the workload, where they need to have a different system for blockchain, for security, natural language processing, machine learning. How are they going to deliver this? And the answer is that, you know, Facebook, Amazon are looking at an ecosystem of chiplets that they can use to create different SKUs, different sub-specializations of systems in order to deliver on these different workloads. In terms of the economics of this, we've already seen this kind of major economic move before. This was what we used to call the attack of the killer micros. That was coined by John Markoff back in 1991, where we saw our vector supercomputers, the classic Cray machines. We were not able to reinvest enough in technology development to keep up with the rate of improvement being achieved in the broader microprocessor industry. And when we saw this curve here, we knew the game was up. The jig was up for full custom HPC systems. And so if you can't beat them, join them. So what we did was we reinvented HPC to utilize microprocessor technology in massively parallel machines, message passing machines. And we leveraged this Branscombe pyramid here on the right, where 80% of the market is supporting, you know, the broader market is supporting 80% of what we need for a supercomputer. And that allowed us to focus our resources on that little tiny pyramid on the top, that 20% that makes a difference, that converts just a regular microprocessor system into a supercomputer through high performance interconnects. And that's been, it's a technological model, but it's really about the economic model for sustainability for HPC. But now we fast forward to today. And so why do I care what Facebook thinks about supercomputers? Well, this is why. We allied ourselves with the microprocessor inventors, you know, creators, IBM, Intel, and stuff like that. And we innovate, you know, on top of that big broad market that they created But now we look at who controls the computing market today, and it's the hyperscale data centers. It's Microsoft, Google, Amazon, Facebook. We need to learn what kind of supply chain they are setting up for themselves in order to deliver their next generation of data centers. And we need to learn how to slipstream new Branscombe pyramid that enables us to leverage the supply chains that are supplying the folks that control the market. But still focus on that 20% on the top where we can innovate and differentiate HPC as a sub part of that overall market. So this is where we're really interested in the emergence of these open chiplets marketplaces. They're not here yet, but the foundations are being developed. This is something that the hyperscale data centers are very interested in, and I, as a HPC practitioner, am very interested in. This is ODSA from the Open Compute Project and the UCI Express are creating these kind of open die-to-die interconnects that enable us to co-package chiplets that come from third parties, maybe even multiple different sources in the supply chain. This leverages an economic model that's under construction, and a lot of the hyperscalers are investing in that. And so we want to leverage this baseline and we want to extend it for HPC because, quite frankly, HPC's become too small to attack the city. $3.8 billion program, we can't do that just every day. So this is, again, the 80-20 rule is still in effect here, but we want to build on a library of reusable accelerators and or chiplets to enable interoperability and sustainability for our market, again, leveraging what the rest of the market is doing. You guys probably already know plenty about chiplets, but this is the necessary slide. It isn't rocket science, but it was really hard. It's basically that we don't have a Moore's law for increasing the number of pins on a chip. We got a Moore's law for cramming more transistors on there, but the pin growth rate has never been up there. And so we, because we didn't grow the number of pins in the package, we grew the SerDes rates. And it's getting to the point now where the power consumed by the SerDes to escape off of the chip is kind of getting close to what the compute energy consumption is. 100 gigahertz SerDes, when Dennard scaling left the rest of the chip operating at 1 gigahertz since 2005, it's a no-go in the long term. So, if you go to the solder microbumps, it's kind of like what we did in HPC, where we, instead of going to a faster and faster individual processor, we go wide and slow. We have slower microprocessors, but a lot of them operating in parallel. So these solder microbumps and the copper micropillars enable you to get bandwidth and performance through parallel scalability and density rather than from increased SerDes rates. And so then the next step is, okay, so if I actually dice my chip up into these little chiplets, maybe not only can I get more bandwidth in a larger package, I can also mix and match the things that I put together in that package. And indeed, you can see there's, I don't want to imply that this is the only way that chiplets or advanced packaging works. There's lots of different kinds of advanced packaging that we can pursue, which leads to very interesting test problems and also pervasive built-in self-test and self-healing capabilities, which we'll need for this all to be successful. But you can read all about that in chapter 22 of the HIR roadmap. But these chiplets are actually already in our production machines. This is the chiplets and the advanced packaging is what enabled us to reach exascale with the AMD solution with an OLCF Frontier. That co-integration, one of the things that we also talked about in the 2009 report was that data movement actually is one of the dominant loss leaders in terms of power consumption. being able to take stuff and integrate more of them together within the package and reduce the length that data needs to be transported over copper wire is one of the things that was a crucial technology for keeping the power budgets down. And you can also see ALCF Aurora, which is the Intel-based exascale machine that's being constructed right now at Argonne. Also EMIB, all of the Intel advanced packaging co-integration technology. But these are all in-house proprietary chiplets die-to-die interconnect technologies. The thing that's and it works great. It's actually reducing power, reducing costs, and increasing the die area we work with. This is a study that was presented at ISCA by AMD in 2021, where AMD basically laid out why they are going with this chiplet strategy. They looked at like a monolithic reticle limited die, and that's the 1x cost there. If they dice it up into 4 die and separately test them so that you get known good die and then co-package those guys together, it's about 60% of, it's a significantly lower cost. But the other thing that they can do is they can grow beyond the reticle limit in terms of area. And so there's even like a standard that's under discussion now to do, instead of the current 2 by 2 centimeter package, to have a 4 by 4 centimeter package. Because as I said, as Moore's law, the transistor densities are slowing down, we're seeing the package area growing at 20% per year or more in order to make up for that loss. So that's why companies like AMD and Intel are using this, and we've had discussions for the past 3 years as part of our post-exascale study, which we started up with AMD about, hey, what if we had a science chiplet and we put that science chiplet into your package? And actually, some of the preliminary design studies we did together with AMD, it looked promising enough that now it's public record. The AMD CTO said, we'll reserve a spot. We can pop off one of our GPU or CPU tiles and you can put your own chiplet in there. And so they're kind of opening up their ecosystem to outside IP to co-integrate in order to specialize the AMD package for other markets. And so that's very exciting. But this is where we come into, we can do it within the current ecosystem that's created by Intel, work with Intel, do it within the current ecosystem that's created by AMD and create a chiplet that's specialized to AMD. But the ODSA and the UCIe are looking at a broader play in the ecosystem, which is to standardize these die-to-die interconnects so that any third party can play, and you can use an OSAT to co-integrate those chiplets together to create specialized solutions with a reasonable budget. And so, the ODSA, but I know the UCIe has a similar vision, which is this creating an open chiplet marketplace to deliver for the hyperscale data centers where they have these open die-to-die interfaces. They have reference designs and the specification for the internal self-test and how you manage the resilience and self-healing of these chiplets. Because once you co-integrate them, you're not going to take them back apart again. So it's got to fail in place and ride through failure. And reference workloads, which include everything from the foundry to the software stack to the back-end manufacturer to create these modular form factors. And this is what the hyperscalers are looking at, this open chiplets marketplace, but we're looking at it also for HPC, where we can have access to commercial IP, very high performance processors, memory, SerDes. We can add in specialized processors for the FFTs and the QR decomposition and the kinds of scientific kernels that are important to us in HPC. And we have massive data movement capability within that package to support image processing, high throughput machine learning, and all the kinds of applications that we want. And then again, mix and match with these modular packages to deliver on a wide range of targets. Oops, I'm pressing the wrong button. Let's go forward. And the other important part of this is IP reuse. As you all know, The loss leader isn't fabbing the chips, really. It is the design and verification that the chip is correct. And designing it to start with is extremely expensive. So one of the key learnings from the past 10 years of specialization is that IP reuse is crucial. With Moore's law kind of tailing off, once you create a specialized accelerator and you verified it, you can reuse that IP over and over again. Better yet, you could actually, once you make the chiplet, you could just dive into that chiplet drawer for a pile of chiplets that you fabbed with it, and you reuse that thing over and over again. But we went from virtually no IP reuse to having many, many different kinds of specialized accelerators in the market. Like the Apple A8 chip has something in the order of 50 different discrete accelerators that are neither GPUs nor CPUs that are co-integrated in that chip. So with IP reuse, we can make specialization affordable by keeping that IP around and growing our library. So we're not going to create the specialized supercomputer in day one. This is going to be a portfolio of acceleration that we build up over a long period of time. Even the hyperscalers can't afford to specialize overnight, but IP reuse is the other key feature of this. All right. Doing time check. Anyway, so they have like a lot of people are really, really interested in making this happen. Same is true for UCI Express. I forgot to update the slide to say that basically nobody's sure which one's going to win, so we're going to play both until we find out who the winner is. All right. So now I'm going to switch gears and talk a little bit about co-packaged optics before I, shut this thing down on time and under budget. So it's one thing to do specialization within the chip, and co-packaging and heterogeneous integration is great for what happens within the chip. But when we have a supercomputer, we have tens of thousands of chips that have to be able to speak to each other at high speed. And moreover, when we look at the system level, we see a lot of diverse resource requirements for fungible resources like memory and storage and for example, GPUs. For instance, in a training configuration, this is data that we got from Microsoft, but also from NVIDIA. For training configuration, you need to independently train on each of those separate GPUs and then exchange weights on a regular basis. And so that's why they build these big DGX nodes with NVLink from NVIDIA, and they have the massive number of PCIe links on the AMD type GPUs. And so that's for scaling up training, but also to attack larger and larger training networks, like these transformer and natural language processing networks. But when you want to do inference, suddenly all that bandwidth you've got inter GPU is wasted. You want to connect all of your bandwidth to the outside world and stream it through that trained model as quickly as you can. So that ends up being a different system, a different set of racks, because you need to reconfigure. When you want to do data mining, you want to connect to your storage subsystem, and when you want to do graph analytics, then you have to have massive internal bandwidth between nodes and also to the high bandwidth memories. These end up being completely different racks, and any resource that you underutilize, we refer to as marooned resources. There's a lot of waste in the hyperscale data centers. There's something like 35% utilization rate because of the marooned resources in the data centers. If we even look at introspect into the HPC workload, what we see here is we buy all of our nodes with the same amount of memory. So this is our older system. It has 128 gigs of memory in each node, and 15% of our workload needs absolutely every bit of that memory. But at any given time, 75% of our workload is using less than a quarter of the memory in each node. And all that memory is consumed capital cost for us to buy it and not use it, and it's consuming power as it idles there in the node, even though we're not actually utilizing that capacity. So memory, this is what drives the working towards disaggregation. This isn't new. These are slides from, I can't remember if it's from Intel or Facebook, but they use the same slides. But the notion here is, the old school way of doing a supercomputer or a hyperscale data center is you cram everything that you think you might need into each pizza box node, and then you replicate and repeat, and you scale it up to be a big system. Disaggregation, though, you're basically taking those resources and you're pooling them, and then when your workload says, I need this much of the GPU, I need this much of the memory, you pool and compose into customized nodes or solutions to deliver for your workload. Now, this is all fine and dandy for some of the hyperscale data centers. They're using currently solutions that use PCIe or InfiniBand or 100 gig Ethernet in order to create this kind of interconnect for disaggregation. But that's 1 to 10 gigabytes per second kind of bandwidths. For HPC, we are operating with memory subsystems that operate terabytes per second bandwidth, and our codes are extremely sensitive to bandwidth. So we need solutions that deliver us disaggregation, but at 100 gigabytes to terabytes per second of bandwidth, with constraints in the latency as well. And that's very hard because, as I described earlier, package performance is pin limited, and Rent's rule tells us how many pins we get in the package, and it's considerably less on this exponential scale than the number of transistors we could cram into a package. And that bandwidth gap has been growing over the years. We've tried to keep up with SerDes, but this is a package from the DARPA CHIPS program, Gordon Keeler. Data from NVIDIA showing that the amount of off-chip power going to the IOs is starting to catch up to the total amount of chip power dissipated overall. And this is not a sustainable path forward. And so that's where photonics and co-packaged optics comes in. There's an amazing, with the advanced packaging technologies that have come online, which initially was focused on the high bandwidth memory and co-packaged memory to get memory bandwidth. We're using those same technology advancements to break out of the package using photonics. It's been an amazing amount of impedance matching. So first, we've got our in-package integration. Instead of going to higher SerDes, having larger pin densities or bigger pin densities, now we can go wide and slow. We don't have to operate at 100 gigahertz SerDes. We can operate at 10 gigabits per second, which is the energy efficient operating point for this kind of technology, which happens to impedance match with these silicon photonic ring resonator technologies and other photonic technologies. The difficulty with photonics was that it is most efficient when you do dense wave division multiplexing, lots of wavelengths operating at a slower rate. But when you had to impedance match 100 gigahertz SerDes with that, it just wasn't working. Now, if we co-package the optics, now we can afford to direct drive hundreds of these little ring resonators, each at a different frequency of light, operating at a much slower rate, 10 to 20 gigahertz, but deliver terabits per second per fiber. Now we can start breaking out of the package at terabytes per second bandwidth, which is better matched with our memory technologies. And then the last and the final thing, and this has only happened in the past 3 to 5 years, all of this is fine and dandy, except if you have to also have individual indium phosphide laser, one for each frequency of light, this thing is not happening. That is way too expensive. Well, IBM did it, but IBM does a lot of things that nobody else can afford to do or can figure out how to do. Co-packaging lots of indium phosphide lasers into the same package. Here we now have comb laser sources where a single discrete laser can generate a frequency comb that contains hundreds of different frequencies of light, all from a single laser. Now we can afford to co-package the laser with the silicon photonics and integrate in the package and get that terabytes per second of bandwidth out of the package. And so, instead of having co-packaged memory, we can imagine, because there's a limited amount of area, that's prime real estate around the GPU there, we can actually instead have a photonic system and package, co-packaged, and we can break out of the package at that terabytes per second bandwidths that we need. And now we're not limited. Now we are not limited to what we can fit into the package. We can now, once you go from the electronic to the photonic domain, you can get anywhere in the rack or the system. mostly the rack because latency issues, but so we can imagine having these photonic MCMs, multi-chip modules where we can pool our resources, and we can use optical circuit switches in order to affect this reconfiguration. So rather than having to operate 4 different racks in a system, we can have the same pool of resources and wire it up dynamically at job startup time to deliver on all these different workloads. So that's it. I'm going to just say, this is the future of computing. We're going to slipstream behind the hyperscale data centers. We need to think seriously about how to put specialization productively to use for science, because the hyperscalers are only going to specialize for themselves. But we can leverage the learnings and the supply chains that they create. This requires deep understanding of our applied mathematics and the underlying algorithms, so that's going to change the way that we design systems. We need to reevaluate our business and economic model for the future of HPC, and we want to model climate and solutions for the global climate crisis without having energy budgets that contribute to the global climate crisis. So yeah, go carbon neutral HPC by 2030. And that's it. Thanks.
Thank you, John. That was fantastic. We do have time for maybe 2 questions. If folks in the audience here want to ask a question, stand up and find your way to a microphone.
You have, seeing if anybody dares to ask a question. Don't be shy.
I'll get us started. So if Art DeGius were here, the CEO of Synopsys, he would love this last slide to finish on, because he always works in a pitch about climate change to every technical community he talks about, indicating that we are responsible for refining the models, but we're about to be responsible for causing
it. Yes.
So in terms of, the last goal for 10 years was to get to exascale. Is the goal for, you said it's not going to be to get to zettascale.
Yeah.
Is it going to be to get to more energy efficient computing? Is that really the driver?
Well, okay, so we have to change our metric for success to be more specific. In the case of climate modeling, for example, we are, even with exascale, not able to get to the point of cloud resolving models. Right now, the models are coarse enough that you can't actually see an individual cloud in the grid. And so they use this statistical parameterized view of clusters of clouds that might be in that grid cell. This is the biggest source of error in our current models. So our metric for success will be to be able to deliver a machine that can do cloud resolving models, where we treat clouds as individual first principles physics, and do so within a budget. But that delivering on a cloud resolving model, as opposed to the number of flops that we deliver, is going to be the new metric for success, not flops alone.
Great. Okay. Anybody else?
Should I grab this mic?
Yes. Introduce yourself, Nirmal.
Yeah. This is Nirmal from NVIDIA. So I want to go with your first bullet, and by the way, great talk.
Thanks.
So I think I totally agree with the first bullet. So now I have agenda.
Okay.
What gets qualified as an exascale supercomputer is based on, as you are well aware, the HPL benchmark,
Yep.
which is high performance LinPack.
Yep.
And what that does is creates an arms race to have this matrix multiply operation. It takes enormous silicon to hit that goal. But if you look at the mix of HPC applications, majority of the science applications have very small smattering of the DMMA or matrix multiply, FP64. So I think what would be good, again, following the first bullet, is to create a benchmark that is representative of scientific applications, and then set the goal of exascale. Because if you go back and do those scientific applications with the current matrix multiply, it won't hit the exascale goal. Although AI may, because AI does at a lower precision. So I think my proposal or request is we should really seriously think about how we qualify scale out systems as exascale and have a true mix of
Yeah.
applications. in the
No,
benchmark?
I've worked for many years for Horst Simon, and one of the group leads, former group leads, he retired, Eric Strohmeyer. They were the co-creators of the LinPack benchmark originally, and it's true. The only reason I've continued with the LinPack benchmark is it's the only benchmark that has that long history that they can actually trace. And if you go to the top 500 site, the most interesting stuff isn't actually who was number one in the list, but all the other ancillary data that they've collected, which is why they continue with the top 500 list. But the code I worked on for the black holes, for example, was adaptive mesh refinement. And Phil Colella, who we worked with, and Mike Norman, who was my group lead at the time, we said the most efficient flop is the one we don't execute. And so sparsity has been a great way to grow performance exponentially by limiting where we apply computation to only where you need it. It's been extremely challenging, though, to come up with that benchmark that reflects sparsity, because there's so many different ways to achieve it. They did put forth this HPCG, which is now part of the top 500. I have my concerns about it because it is neither sparse, it does not exercise the interconnect, and it says that flops aren't important, memory bandwidth's important, and that's not really telling the full story of sparsity. There have been many attempts to replace LinPack, and so people are actively trying to do that. Very few have been successful. So I agree with you that we need a new arms race. I think that seeing Eric Strohmeyer's analysis, that one that shows we're only going to get 10x after 10 years, is kind of the battle cry that we can no longer make flops the metric for success. Neither can we make bandwidth. It's going to have to be delivered performance for a high value application. And
All right, let's cut it off there. Let's thank John again for a great keynote.